So next we shall continue with fourth question in the series of 5 marks question or section D questions. Already session 1 you might have seen that 3 questions I had explained. Now we shall go with the fourth question. Obtain an expression for electrical conductivity of conducting electrons in a metallic conductor in terms of charge E and mass M. So this is also a very important question. Easy derivation. So let us see the derivation. So I have drawn the necessary diagrams and I have written it. So first to start with, you need to draw a conductor connected to a potential difference across its ends as V, that is to a cell or a battery. Length of the conductor is L. The drift velocity of the electrons is denoted by Vd. So this is the drift velocity of the electrons. And then the electric field is denoted by E. Current through the conductor is denoted by I. And the area of cross section of the conductor is denoted by A. So same thing I have explained it, I have written it in terms of sentences. Next let us see how to derive this. Now generally this can be also asked to in another way. Obtain an expression for conductivity by using the expression for drift velocity also. It also will be the same answer for that question also. Now to start with, we know that relation between I and Vd, that is current under the drift velocity. So this is known to you people. What is the relation between them? That is, what is the relation between I and Vd, that is the electric current and the drift velocity. So that is I equals to that of Ne times AVd, where what do this symbol stands for? This symbol stands for number of electrons, charge of an electron, area of cross section and the drift velocity. So this derivation is also there in 3 marks. It can be asked for drift velocity and relation between current. That we shall see in the other section, not in this section. Now this will take it as equation 1. So this should be like a subscript. It should not be like an individual letter. It should be like a subscript. So always it is better to write it little small so that it becomes like a subscript. Now next, in this expression, let us substitute the expression for drift velocity. Now we know that drift velocity Vd equals to, again this has to be like a subscript only. We will stick on to that. You also should stick on to that. If you write it like a letter, it will lead to confusion. So Vd is equals to that of E into tau by M. So this is the expression that we get for drift velocity in terms of charge of an electron, magnitude of the electric field, relaxation time and mass of an electron. Now relaxation time is also another definition where we speak about the average time between two successive collisions of a drifting electron. Now when it comes to drift velocity, it is a velocity with which an electron drifts under the influence of an electric field. So this I take it as equation 2. Now what are we going to do? We are just going to substitute equation 2 in equation 1. So that way it becomes I equals to that of N times E, A into, in place of Vd, E times tau divided by M. So what, nothing much we have done, just substituting the value. Now if it simplifies, this becomes N times E square, E into E becomes E square, A times tau into E by M. So this is the expression for current that we get from this. Now we are going to use the concept of current density because that is the one which relates conductivity to this expression. That is why for us to have a current density, we need to have the expression of I by A. So transpose this A to the LHS. So that implies I by A is equals to that of N E square tau times E divided by M. Now like I said, I by A is the current density, that is J vector form, if I write it, it will become as, so in the vector form, whatever you have written it is in scalar form there, we don't have any vector form there. So J vector equals N E square tau by M times that of electric field in the vector notation. So since I have written a vector notation, I have also written the electric field in terms of vector notation. So this I will take it as equation 3. Now we also know the relation J vector equals to that of sigma times E vector. Now conductivity we can define, let sigma be the conductivity, but we are not written in that. So here I have introduced this where sigma stands for conductivity. Now this is equation 4. Now if you compare equation 3 and 4, LHS are equal, their RHS must be also equal. So from 3 and 4 what do we get? So most of you will be knowing that is N E square tau by M into E vector is equals to sigma times E vector. Both are same quantities, so it will get cancelled. If I rearrange this and write, this will become sigma equals to that of N E square tau by M, that is the expression for conductivity is given by the product of number of electrons in the conductor, square of charge of an electron, relaxation time whole divided by mass of an electron. So this is a very simple and easy derivation. We start with the expression for current in terms of drift velocity. We then substitute the value of drift velocity in that equation, and then we rearrange this only for the purpose of getting in terms of current density, and then we write the definition of, by definition of current density, we write this expression derivation, that relation also has 3-mark derivation that we shall see in the other section. Then equating it and cancelling the terms on either side, we will get an expression for conductivity. So the next question is, assuming the expression for drift velocity, derive the expression for conductivity of a material where symbols have their meaning. This is the same question as previous question, only rephrased in a different manner. So the answer is same. So whether it is asked like this or in the previous way, for both the questions the answer is same. Now next let us see 6th question. Obtain the expression for the force per unit length between two infinitely long straight parallel current carrying conductors placed in vacuum. Hence define the unit ampere, or it can be also rephrased as obtain the expression for force per unit length between two infinitely long straight parallel conductor carrying currents and placed in vacuum. What is the nature of force between the two conductors if the currents are in opposite direction? So this part we shall discuss once we finish the derivation. Let us get into the derivation. So here we have two conductors, conductor 1 and conductor 2, through which currents I1 and I2 are flowing in the same direction, and the distance between them, that is the distance of separation between conductor 1 and conductor 2, is denoted by D. Now rest of the things we shall discuss and then involve it in the derivation. First to start with B1 and B2. What are B1 and B2? Both are magnetic field. B1 is the magnetic field due to the current I1 in the conductor 1. So this conductor 1, since the current is flowing through it, there will be a magnetic field around this, and that field value at the point on the conductor 2 is B1. Similarly, the magnetic field due to the current I2 on the conductor 1 at this point is B2. And then the magnetic field at the point, any point on the conductor 2 will be into the plane. So this is by right hand thumb rule. And then again, the magnetic field at any point on this conductor 1 due to current I2 will be out of the plane. So that is why the arrow marks have been written like this, and I have marked it by the direction of into and out of the plane also. Now, magnetic field at any point on conductor 2 due to I1, that is current through the conductor 1, is given by, so that is denoted by B1, that will be equals to mu naught by 4 pi into 2I by R. It is generally B is equals to mu naught by 4 pi into 2I by R. Since here the distance of separation is D, we will take D, and which current generates this or produces this magnetic field? Current I1. So this I will take it as equation 1. Very simple. This is written from this expression, that is B is equals to mu naught by 4 pi into 2I by R, where R is taken as the distance, but here you have taken the distance of separation as D. Therefore, this expression will change to whatever written on the board. This is the magnetic field due to current I1 at any point on the conductor 2. So similarly, and already I told you that is into the plane and it is out of the plane. So here if you want, this is due to the current I1 which is into the plane. So if you want, you can mention it here. B1 is into the plane. Then similarly I can write magnetic field at any point on conductor 1 due to the current I2 is given by, so that will be B2. So that is B2 is equals to mu naught by 4 pi into 2 I2 by D. Same distance, so denoted by the same expression. Nothing much will change here. So we will write with the same denotation only. So nothing much we have done. We have only written the expression for magnetic field exerted by the current conductor 1 on 2 and conductor 2 on 1. So this involves about what? Finding an expression for the force per unit length. So basically we have to come into the concept of force. Now we know that the force are exerted by conductor 1 on conductor 2 as well as conductor 2 on conductor 1. So let us say the force exerted by conductor 1 so the force exerted by conductor 1 on conductor 2 is given by, so we denote it by F21, so that will be equals to that of the current passing through that conductor itself, which is the conductor 2, and the cross product of the length and the magnetic field due to conductor 1 on conductor 2, so that is B1. So many of you might be thinking that why not B2 here? We cannot take B2 because this is the force exerted by magnetic field of the conductor 1 on conductor 2. So this has to be B1 only, not B2. So I repeat again, if I write it likewise, the force exerted on the conductor 2 by conductor 1 will be given by current passing through the conductor 2 times that of cross product of the length of the conductor. Since we are taking the length to be same for both of them, the length is denoted by L. It is infinitely long conductor, but still we can take the length of any particular length we can take to be equal. A part of that we can take it as equal length for both of them and denoted by L itself. Now we know the cross product where we will be writing it as, that is F21 will be equal to that of only the magnitude. If I write, that will be I2 B1 L sin theta. Now theta is the angle between the conductor, that is the current flowing through the conductor, and the magnetic field. So here, if I take for the maximum force, that will be for theta equals to 90 degrees. For theta is equals to 90 degrees, this expression will become as F21 F21 is equals to that of I2 into B1 into L. Now if I take this as equation 2, now I substitute the value of equation 1 in equation 2. So that becomes F21 equals to that of I2 times L. B1 I'll substitute now, that is mu naught by 4 pi into 2 I1 by D. So if I rearrange this and write, so this is substituted one, so I put it in brackets, mu naught by 4 pi into that of 2 times of I1 I2 by D. Usually rearranging we do it so that we write it constants like first. That's why I've written it like this. So F21 we have an expression, and this I'll mark it as equation 3. So this is equation 3. I missed one term in this, that is the length. So I'll write that term, that is length. So some of you might be thinking, if it is unit length, because force per unit length is asked, why are we keeping the length here? I will explain you at the last why length is necessary here. Why are we not taking L as 1 and then we are not writing L here? So continuing like this, for the other force. So now the force F12, that is the force on conductor 1 due to conductor 2, will be equal to that of current flowing through the conductor 1 times L vector cross B vector of the magnetic field of the conductor 2. So again, if I write this, this becomes F1 B2, sorry, I1 B2 L sin theta. Again here theta, if I take it as 90 degrees, this expression becomes only the magnitude I am writing. So that will be B2 I1 L, so that becomes 1. This again, if I substitute the value of B2 in this equation, that is in F12, you can also put a number to this. Previously we had numbered it till 3, so I can take it as equation 4 also. You can write it likewise also, both are fine. So if you people want to say no, we will follow the same method, we can just write substituting equation 2 in 4. So for which we need a number 4, this is equation 4. Then what do we get? We get F12 is equal to that of I1 into L. Substitution is being done. So this is mu naught by 4 pi. Remember, the current, the magnetic field acting on that will be due to the current of conductor 2, not 1. So 2 I2 by the distance D. Already we have derived this. I am just reminding you people. Now if I rearrange it and write, this will be again mu naught by 4 pi into 2 times of I1 I2 by D times L. So this is equation number 5 I take. So from 4 and 5, what can we conclude? From equation 4 and 5, the magnitudes of these two forces F12 and F21 is same. That let us take it as F, that will be equal to that of mu naught by 4 pi into 2 times of I1 I2 whole divided by T times L. So this is the same value, right? So since both of them have same magnitude, I have written it like this. Remember, they have different direction or opposite direction, so that we can write it at last by in the vector form. So this is the magnitude. So magnitude can be denoted by this. Now comes the important part, like what we were discussing about force per unit length. Now what I do, this implies I bring L to this side, that is F by L. That will be equal to that of mu naught by 4 pi into 2 times of I1 I2 by D. So now you can see there is no L in this expression. That's why I said at the last I'll explain you people. It is asked force per unit length. So basically you have to divide the force by length. You will get force per unit length. And you know, even while defining, which you would have already done several times, you would have told about the Newton meter. Where does the meter comes from? F by L. So this is the actual expression for force per unit length acting between two infinitely long parallel conductors carrying currents in the same direction. They are carrying currents in the same direction, so it is an attractive force, and the expression for that is given by this. So in case if you say I want to take unit length as 1 meter in the beginning, I will not be writing L into this. That is up to you. You can also do that, but you need to mention if I consider per unit length you have to take, but then in the definition you will get little confusion. That's why I would not suggest this. So this is the explanation and derivation for this. Now by using this, how do we define 1 ampere? That is an interesting task. So I always suggest this way of defining to be very simplified form. So 1 ampere I am going to take. So which means what? I1 into this you should not write, whatever I am writing here you should not write in your answer. So I1 and I2 both should have to be 1 ampere. Now if this has to be equal to the force per unit length or whatever you are going to take in this consideration, we need to take the distance as 1 meter. Even if I take distance as 1 meter, if I take the distance as 1 meter, so this entire term will be 1 itself. Then mu naught by 4 pi, we already know what is the value. That is mu naught by 4 pi is equals to that of 10 to the power of minus 7, the value. Now by using all this, we can define 1 ampere. Now how do you define 1 ampere? 1 ampere is a steady current that flows through each of these conductors. I repeat, 1 ampere is the steady current that flows through each of the conductors that produces a force of 2 into 10 to the power of minus 7 newtons per meter. You see here Newton force is measured in Newton, length is measured in meter. So 2 into 10 to the power of minus 7 newtons per meter when they are separated by a distance of 1 meter. So it is a very easy way of putting it, and I also suggest to people to learn in the same way. How to write this? 1 ampere is the steady current that flows through each of these conductors which are separated by a distance of 1 meter that will produce a force of 2 into 10 to the power of minus 7 newtons per meter. Since they are flowing in the same direction, it will be an attractive force. If they are flowing in opposite direction or anti-parallel, then it will be repulsive force. So there was a part of the question which asked what will be the force if they are in opposite direction. Basically they will be repelling each other, or it will be a repulsive force. So that's the derivation. Once you write about B1, follow the same for B2. Once you write about F21, follow the same technique for F12. So it is basically once if you write field, once if you write the force, other thing is the same. And then at last, since the magnitude is same, we take it as a force as F, and F by L is the actual thing what we are supposed to derive, force per unit length.